it says it's not about the API. And I want to get your thoughts on that, Mason. We all want to know. Give us a round of applause. You're going to have your timer, no problem. Would you like this podium mic or more freeform?
I'll take this.
More freeform.
And then, does this go backwards and forward?
Yes. So this is the big fat green button for next. The red one is back.
Awesome.
And if you want points, you can also do that.
Awesome.
Okay. I'll get this for you. Yeah. Enjoy.
Hey, thanks for the introduction, Abner. Thanks for having me again. Always look forward to Handmade. It's one of my favorite conferences. So yeah, let me get this started for you guys. I'm Mason Romali. I'm an independent game developer, a board member on the Zig Software Foundation. And in the past, I taught grad and undergrad students to make games and game engines. Like Abner mentioned, I shipped my game Way of Rhea in May, and I learned a lot from making it. Talk more about that in a talk at Sickle you can look up on YouTube. But one of the kind of outcomes there is I decided I want to build a new engine for my next game. Way of Rhea was built in OpenGL, and as many of you are probably aware, there's a bunch of new APIs that are replacing kind of the old style graphics APIs. And so I decided if I'm making a new engine, it's time to take a look into these new APIs and see if it's time for me to upgrade. So that's what we're going to talk about today, graphics APIs. How many of you also know OpenGL? How many of you are comfortable with the new modern APIs? Okay, so we got like that's good. So we got a bunch of people. For the people online who maybe can't see the hands raised, a bunch of people used to the old APIs. Maybe not as many with the new APIs. I hope this will be maybe informative to people working with the old APIs, thinking about trying out the new APIs. This is my, I don't know, maybe it's my 5 or 6 month journey looking into them. So yeah, let's start off with, I think we all have a sense for this, but let's talk about what a graphics API is. It's supposed to be a picture of a graphics card there, but it's not really a big deal. You all know what they look like, and if you don't, it's that box in your computer that makes it go fast. Yeah, this is what it looks like when it doesn't do its job. When you're not good enough at Vulkan. So yeah, I mean, a graphics API is a way to talk to your GPU, right? You can't just go run x64 on it. You can't well, there are actually ways you could run C on your GPU, but not in the normal way. You're not going to compile a Windows executable file and run it on your GPU. So a graphics API is essentially just a protocol that you use to talk to the GPU. Now, the thing is, there's a few different GPU vendors, right? And since there's a few different GPU vendors, you get a few different graphics APIs. Well, are you telling me those aren't GPU vendors on the screen? Wait, are you telling me that there's 3 different graphics APIs and 3 different GPU vendors, and all 3 GPUs support all 3 APIs, but which ones you get to use depends on the operating system you're running? That's a fundamentally silly situation to be in. Unfortunately, we live in a fundamentally silly world. So yeah, you could have your MacBook, and you could reboot it into Linux, and now you need to use a different graphics API to talk to the same graphics card. And also, all of these APIs are exactly the same as each other. Like, if you're worried about which one to use, it doesn't matter. They're this, like, details are a little different. The windowing system integration is different. They do all the same stuff because it's the same hardware. So today, we're going to be talking about Vulkan because it runs the most places and it's managed by a nonprofit. But if you're not working in Vulkan, all the same stuff's going to apply. It's literally like these APIs are almost identical. In particular, I'm interested in, for my game, I want it to run everywhere. I mean, that's not true. I want it to run on PC platforms, and I want it to run on consoles. And as part of that, I'm building like a GPU abstraction library, like everyone ends up doing, because you need to support all these APIs. And so whenever I'm adding a new feature, I'm checking like, okay, what would it look like in DirectX? And the answer is exactly the same almost every time. So yeah, if you're doing DirectX, no problem. We're going to do a brief history of graphics APIs here. I wasn't around for most of this, very hazy details, but I just kind of want to build to like why we have the modern APIs we have today and what's different about them. So in the early days, we had vendor-specific APIs. If you wanted to run a certain graphics card, you'd use the API for that card. Makes enough sense. But there's a downside, which is kind of familiar, where you have to use a bunch of different APIs, right? If you want to support multiple cards, you end up writing multiple APIs, and that's kind of a pain. Around 92, one of those APIs, RSGL, became OpenGL. It was released as an open standard that other other graphics card vendors could implement, which is a really great idea, right? Because now you can write one API and run it everywhere. But this idea has one fatal flaw, and the fatal flaw is that it's a good idea. And you know who doesn't like good ideas? Yep, Microsoft. So Microsoft, of course, had to make their own OpenGL and call it DirectX. So you still end up with two APIs that are the same as each other. Around 2004, we started moving away from fixed function to the shader model. The idea here is that you could write, with the fixed function model, you're kind of just like configuring your GPU to do specific things. With the shader model, you get to actually start running. I think you could do this before, maybe with some kind of like assembly or something. But with the shader model, you can actually write like a text program that runs on your GPU and does nice special effects and stuff. Maybe you want to make a shiny object or a bumpy object. You can just like write the code for your game to do that. Gives you a lot more control. Of course, it also like makes things more complicated, right? Like every time we step to the right on this graph, things are gonna get a little bit more involved. If you're just doing fixed function, you just kind of tell the graphics API to draw some stuff and it does it, and that's it. Here you have to write a bunch more code. Around 2014, we started getting the modern APIs and they become increasingly relevant. The idea is that, people are doing more and more stuff with GPUs, and it's not necessarily just graphics. In a way, GPUs are just kind of giant SIMD machines. Single instruction, multiple data set. You have maybe a multiply operation, and you want to do it on a bajillion inputs on the same time. It's the same operation, but there's a lot of different data. And graphics is really amenable to that kind of optimization, but there's lots of other things that can be done quickly that way. And people want to use GPUs to do all kind of cool stuff. So GPUs, the GPU APIs got a lot lower level. You got a lot more control. You got the ability to do way more with them, but as such, they got more complicated, harder to work with. So let's look at this triangle here. We're going to start in a fixed function OpenGL sample I found online. So I know you all probably can't read this from there, but it's about 40 lines of code, and the gist of it is it says here are some vertices, here are some colors, and then let's just like loop and draw that triangle. And even if you're not a graphics programmer, if you pull this up at home, you can look at it in a couple minutes, understand what's going on. It's not too complicated. Now, what I'm interested in here is, should I move to Vulkan for my next game? So let's look at the same code, but for Vulkan. Okay, so it's like a little bit longer, but a lot of it's like comments in white space. So it's not really a big deal. Oh, sorry, there's another slide. Okay, so it's like a little bit longer, but most of it's comments in white space. So it's not really a big deal. It's a little more complicated. Sorry, wait, how many pages of this are there? Okay, geez. Okay, maybe I see why people are complaining. Okay, so we took 40 lines and we turned it into, what's that, 1,180 lines? There are some more comments in white space, but not like almost any in this last whole 2 pages. Yeah, so it's a lot more code. There's a lot more going on here. And remember, that's just for this, right? Like this is not what my game's gonna look like. It's gonna do a little bit more than that. So like if that's how much code it is just to make this, imagine what the full game's gonna be like. And also like I'm an indie and I'm making an engine, and like understandably most indies aren't making engines. I'm the only programmer on the team, so it's like I have to build the game. I have to build the engine, and the renderer is not the whole engine. It's just a part of it. I have to build the renderer, build the engine, and build the game, and I'm supposed to do all that just to get a triangle on the screen. I kind of get why people feel like this. So, okay, here's the thing though. You may not like it, but this is what peak performance looks like. Also, it's simpler. All right, what are you talking about? It's simpler? I actually think Vulkan's great. I was not sure that I would think that when I started. And so if you're coming at this and you're thinking, really, 1,100 lines for something that could have been 40? Ridiculous. I'm just going to go use OpenGL forever. That's fine, do whatever you want, but I want to maybe make a pitch to you that it's worth looking into these new APIs and that it's actually not as goofy as it maybe seems at first glance. But I understand that I have my work cut out for me here, and I'm also claiming it's simpler. It's kind of how is more code simpler? So we're gonna start out with some Vulkan concepts. I'm gonna walk through I'm not gonna go line by line. We don't really have time for that, and I don't think it would be particularly engaging. But we're gonna go through just like the core concepts that are like kind of going on that are making it longer. Not going to super deep dive on each of them. There's other talks for like introductions to writing Vulkan, but just like why is it longer? What's happening in all that extra code? Once we have a kind of rough understanding of what's actually going on, I'm going to go over a way of doing fast, flexible, and simple rendering in Vulkan that I'm using in my new engine. It's not the only way to do good rendering in Vulkan, but I want to show you that it is possible to keep things simple while using these new APIs and still benefit from them. And then lastly, this has kind of maybe shifted my thinking a little bit about like APIs and what makes an API good or bad, or how to evaluate one, how to design one, and maybe there'll be some takeaways even if you're not actually a graphics programmer. Okay, so let's start out with some Vulkan concepts. And we're going to kind of compare them to OpenGL, and it seems like a lot of the audience is familiar with OpenGL, so I think that'll be helpful. So first things first, you look at a Vulkan sample, you're going to run into this thing called a physical device and a logical device. The physical device is just the GPU that you're using, and the logical device is kind of like an instance of it that you've configured a little bit. And if you think about like OpenGL, it doesn't really have this concept, right? Like when you're writing an OpenGL app, you just kind of you create a context and then you just like write some code, and you don't get control over what device it runs on, which is kind of a problem, right? Like I got a picture of my laptop there. If you have a laptop, it probably has two GPUs. It probably has your integrated GPU on the CPU, and it has a separate discrete GPU, which is going to be way faster. If you're running a game, you really want it to go on the fast GPU, not the slow GPU. Like, you know, the gamers probably spent a bunch of money on their GPU. If they buy your game and then it runs slow because it didn't run on the fancy GPU, they're not going to know that's why. They're just going to think your game's slow. And that's a pretty sad outcome, right? Like you wrote something that was fast enough and it just ran on the wrong hardware. Well, OpenGL doesn't really have an answer for you. And it's kind of Microsoft's fault. Like I believe DirectX, old DirectX still had a solution for this, but Microsoft didn't want you to use OpenGL, so they never updated their window integration code. But regardless, you couldn't do this in OpenGL, so the sample code's shorter, right? The sample code's shorter because you just literally skip this step. There was a way to do it. OpenGL doesn't have an answer. To be clear, OpenGL games do have a solution for this. The solution is you like declare a weird symbol and set it to a specific value, and then like the driver looks for it. Like there's a way to do it, but it's like mega jank, and like good luck figuring it out if you don't already happen to know about how to do it. It's probably it's not in the speaker notes. Anyway, ask me after if you're like, how do I make that work in OpenGL? I have an OpenGL game. I can show you the line of code. But yeah, so you're gonna get a few lines of code just to like pick the right GPU. But like, I mean, you want to do that anyway, don't you? Next concept, command buffers. So in Vulkan, when you want to tell the GPU what to do, instead of giving it one, you have to remember like GPUs are asynchronous, right? Like it's a separate device. It's not like you're running the code on the CPU. So you're going to have to send a command to the GPU to tell it to do some stuff. At some point, it's going to do it and complete. You don't send one command at a time. You send commands in buffers of commands. And OpenGL under the hood, that's presumably the same thing that's happening. But OpenGL doesn't expose the command buffers to you. So in Vulkan, it's like you have to actually pick like a queue, which is a port on the GPU essentially. Like each port maybe is like better at doing different operations. Like maybe you have a port for transfers, a port for compute, a port for graphics. Maybe you just have one for everything. I think the graphics ones always do everything. And then you have a command buffer allocator, and you allocate your command buffers from there. You fill them up, you send them to the GPU. So it's some extra stuff you're doing to get the commands there, as compared to OpenGL, where you just like send a command, and it makes it more code. And in the triangle example, it definitely inflates the size of our code. But if how many people have shipped something in OpenGL? How many of you reinvented command buffers in your OpenGL app? Like, okay, yeah, almost all of you. Like only like 2 hands went down. So like, yeah, our triangle example is shorter because we didn't need to reinvent command buffers in it. But the reality is command buffers are a super useful structure when you're like, building a more complicated graphics app, and everyone writing OpenGL code is reinventing them anyway. So your actual Vulkan app like didn't have to reinvent them because they already existed in the API. I mean, maybe you have a software command buffer abstraction, but you don't need it. So yeah, I don't need to dwell on command buffers. It seems like you all made your own command buffers anyway, so you should be pretty familiar with the concept. Now you don't need to make them anymore, unless you want to. Okay, we got pipelines. So the idea of a pipeline is you're gonna have the GPU render some stuff, and there's a bunch of ways the GPU can be configured, right? There's a bunch of like fixed function options that you can change. You can also decide like, what shader you're going to run. In something like OpenGL, you just kind of say like, turn this option. You have function calls to turn options on and off. So you can be like, I want to set my blend mode to additive because I want to make a lightsaber and it's going to be all glowy. and then I want to turn it back to normal to render something that's not supposed to be glowy. You just have a bunch of different functions you call to toggle all of these things, and then eventually you call draw. And it's just like a giant state machine. Everything's global. It's kind of hard to manage. In Vulkan, all of these options get baked into a pipeline, and then you bind the pipeline. So say that you have a bunch of particle effects that all are glowy, and they're all additively blended, and they have, I don't know, some of these other settings are set to specific values. You put them in one pipeline, and then you can switch to a different pipeline for your other objects. What's nice about this is you kind of know where the cost is. Right, in OpenGL, you're writing a little bit less code because you can just, at the time you're going to draw the object, set the configuration options. But it's a little bit hard to understand which options are expensive to change and which options are cheap to change. Sometimes you find your game running really slow and you realize, oh, I wasn't really supposed to change that one a bajillion times per frame, and the other option, it was fine to change a bunch of times per frame. And if you really know how GPUs work, I imagine that you would kind of understand implicitly which ones are slow and fast. But me, when I was starting out with OpenGL, I had no idea. I would just have to experiment and ask people online which options are fast, which ones are slow. In Vulkan, you just build this all into a pipeline. So yeah, it's more code, but you're also kind of being a little bit more honest about what the computer's actually doing. We got a few other concepts here. We got the pipeline layout, which is just kind of saying the structure of the data that you send into the shaders. Relates to the descriptor sets, which is like the actual kind of like the uniform data and stuff, like the options you pass into your shader. And the layout is just the layout of that data. I'm glossing over the details because I think all that stuff you can find online, but the point is that this is a useful concept. It's more code you're writing, but often you actually, maybe not as common as command buffers, but it's often that in OpenGL you'd end up creating something like this anyway, just to get away from the massive amount of global state that OpenGL has. Okay, another one we got. Some of the older APIs maybe would have this if they had better window system integration, but OpenGL doesn't really have a concept of it as the swap chain. The idea here is that long gone are the days of rendering pixels straight to the screen. You're going to be rendering pixels into a buffer somewhere that the window manager is going to display on the screen at some point. And as such, there's different strategies that could be used to display your images. For example, you could be using a kind of standard vsync setup. There's details even within that, but you could be using like triple buffering. There's lots of different ways to configure how the images you render are showed on screen, how often they're showed on screen, what order, how deep the buffer is, which is going to affect input latency, and all of these things are going to affect how smooth your animation is, what the cutoff is. Like if you miss your frame, do you have to wait until the next vsync, or like does it show right away but have tearing? There's lots of reasonable trade-offs you can make, but the point is you probably really care about this stuff if you're making games. You probably really care about when your frames are presented, and with exactly what parameters. And a swap chain is just how you configure that. In something like OpenGL, there's some extensions for controlling vsync, but they're never implemented correctly on any of the vendors I've tried them. Like they work, the basics work, but the details never really work correctly, and the user can always override it, and you just don't get a lot of control. I would argue that even in Vulkan, the main swap chain extension, I would like it to be lower level than it actually is. So it's more code that you're writing, but you probably want your animations to be smooth if you're making a game, right? So you probably want to know how your images are being presented. We got synchronization. So yeah, I'm not gonna lie, synchronization in Vulkan's complicated, right? But like we all know that multi-threaded programming is hard, right? Like everyone's aware this is a difficult thing to do, right? And this is not, when you're doing graphics programming, not only are you doing multi-threaded programming, you're doing multi-threaded programming on a separate device from the main device. So like, of course it's hard, right? There's complicated stuff going on. It's going to be a challenge, but like someone had to do the same work to make your OpenGL code work. It just wasn't you. Like the complexity is still there, but like OpenGL had to assume the worst case because OpenGL pretends to be synchronous, right? Like there's like sync and flush, but for the most part, you just kind of write your code and it all just works, which it doesn't, and it doesn't know what you're going to do, which means it's assuming the worst case, and you're giving up a lot of performance. So yeah, you got to spend some time figuring out this, and it is going to result in more code that you wouldn't have had to write in OpenGL, but like you have control over your multi-threading, which you probably want. You're trying to go fast, right? So it's hard for me to complain about that. A big one that I see a lot of people complain about is memory management, and it's worth mentioning here, like I am glossing, like I'm just kind of flying past a lot of details. I have like stuff in the speaker notes that if you're like going home and you're writing, in your like writing Vulkan that might be useful to you that I'm not going to read here because it's just like quotes from the specification and stuff. But there's like, I'll have a link to the slides at the end, and you're welcome to like look at them on your own devices and reference them. But yeah, the gist of it is that when you use something like OpenGL, it basically just gives you a heap allocator, and it's like reference counted memory. And so it is like very easy to get started because it's all automatic. But like, most of you are not writing your game engines in garbage collected languages. So why would you want your GPU API to be garbage collected, right? That's probably not, if you really think about it, like you're used to it, but like, is that really a choice you would have made for yourself? Probably not, right? You'd probably just use like an arena allocator or do stuff per level or something. We'll talk more about that later. Furthermore, GPUs have many different types of memory that are like good for different things. And you do have some flags in OpenGL that control this stuff, but it's kind of hard to understand what exactly they're for, and you only have so much control, and you can't really query like, what does this GPU actually support? You just kind of hint at what you want, and maybe you get that, maybe you don't. In Vulkan, it's very, very manual. You essentially get a page allocator. I don't know if it's exactly correct to call it that, but the gist of it is that you are not really supposed to allocate small amounts of memory. You're supposed to just say, give me a bunch of memory, and I will deal with dividing it up. And on the surface, this is a lot more work, and a lot of people will recommend using something like a Vulkan memory allocator, which is a totally legitimate way to do this. I'm going to kind of make an argument for a simple approach later on, but if you were just kind of to come at this for the first time, you probably would end up with something pretty complicated. But we'll come back on how I think you can do this pretty simply. CPU side, it's not really too different from something like OpenGL. The driver objects, or the driver is going to allocate them how it wants to allocate them. So there are other features. I think those are the main ones that I'm interested in today. The takeaway here is that like the complexity that you see in Vulkan like existed when you were writing OpenGL. It's just that you weren't the one writing it, right? It was a graphics driver implementing most of it. And I think a lot of people, I've seen a lot of people online saying things like, Vulkan's not good for indies. Like, maybe if you're a big AAA studio, it's good, but for indies, it's too much work. And I honestly kind of feel the other way around in that, like, it is a bunch of work, but, you only have to do this stuff once. And, NVIDIA isn't going to meet with me to optimize my game for their new GPU. I don't have that kind of mass audience. It's not going to affect their bottom line. So I don't want to be at the whim of the GPU drivers, right? Like if I write it in Vulkan, I get to decide much more like what's actually happening. Whereas if I was to write it in OpenGL, the GPU is making all these judgment calls about how to interpret my intentions and to try to optimize them. And if you're a big studio, they'll work with you directly. And I just don't really think that's realistic for an indie. So like, I actually think as an indie, having this low-level control is it's almost like an equalizing force, right? Like we all have the option to fully take advantage of the GPU if we can use the GPU at a low level. Whereas if you're writing this high-level API and you're just dependent on making a deal with the company that made the GPU, that I don't know, that feels less fair to me. So yeah, I mean, the complexity's there either way. Someone has to write this code. In the new APIs, it's you. It's more work, but you get to go faster. And you don't have these issues where like your shader worked on one person's GPU and not another because you're the one compiling the shader. All right, so let's get into actually using some Vulkan. So we talk about fast, flexible, and simple rendering in Vulkan. This is, like I said, not the only way to use Vulkan, but this is what I'm doing right now in my engine. Maybe I'll adjust it as I progress on my next game, but it's working for me for now, and I think it is a much easier way than I see a lot of people get started with Vulkan. So we're going to go over my high-level strategy. I'm going to talk about like two lenses through which you could look at this kind of stuff. So one is you could look at like writing your renderer as like programming the API, right? You could say, okay, what is Vulkan capable of, and how do I use that to accomplish my goals? And you could write your renderer that way, but the lens that I'm preferring is what is the hardware capable of? How can I use it to accomplish my goals? And then, okay, great. How does Vulkan let me tell the hardware to do that? It's not that different, right? But I think it results in some better decisions and simpler outcomes, and we'll probably see why in these next few stages. So first, let's talk about memory management. So think about, instead of looking at it like, okay, what functions does Vulkan have for memory management and when should I call which? Let's think about like, well, why are we doing memory management on the GPU? What are we even using VRAM for, right? And probably we're using it to store things like level data, right? We probably have a bunch of meshes and textures and stuff for a level that are, say we're doing a level-based game. We might not be. We can apply this wherever. But we probably have a bunch of meshes and textures and stuff for our level that we need to be on the GPU so we can render them quickly. Well, we could just do one big allocation at the start of the level when you load it, or one per memory type that we need, and then just stick all of the data in that allocation, right? And then when you leave the level, you just free it. Oops. Go back here. And it's what you're probably doing in your engine anyway, right? Like probably your actual CPU code isn't like loading individual files and dropping them all the time. You probably, when the level loads, like put a bunch of, hopefully you put a bunch of data into one big contiguous buffer because it's all going to be cache coherent. It's going to be easy. You don't have to worry about like constructing and destructing individual objects. You're just like, look, that's the memory for the level and it's gone when the level's over. There's no reason the GPU has to be any different. So yeah, I think if you were to look at this from an API perspective, it would be, and you're used to OpenGL, it would be really tempting to sort of recreate OpenGL, right? You'd be tempted to say, okay, geez, it's really tough that there's no heap allocator. I'm going to make my own heap allocator for Vulkan. Now that I've made my heap allocator for Vulkan, let me add the reference counting in like OpenGL had. And now you've just kind of remade and worse OpenGL, right? And you've kept all the complexity. On the flip side, you could just take advantage of the fact that it's low level. You say, great, I only really wanted to load stuff when the level started, so put it all in one big buffer. Very small amount of code, easy to debug, easy to maintain. And you can adapt this to other style games. Maybe even an open world game, great, divide it into chunks. Each chunk is a buffer, load the chunk when it appears on screen and free it when you no longer need it. So yeah, memory management doesn't have to be complicated. There are a lot of details you got to get right. I think the speaker notes where I first mentioned memory management have some interesting stuff. A lot of the tutorials cover this stuff. So yeah, you definitely got to like learn what all the different flags do. You get the stuff right once, and then you can just stick all your memory in a buffer, and you're good to go. Let's talk about Vertex data. It's pretty common in OpenGL, right, to have a bunch of different models with different like vertex layouts. Maybe you have some models that are completely static, and all they have are, you have per vertex, you have positions for the vertex, and maybe UV coordinates. Maybe you're doing some like skinned models, and you pass in some extra data to help with the skinning. And you end up having to tell the API about all these different vertex layouts, and you have to change them in and out. And you could do all of that in Vulkan. But vertices are just data. We could just put them all in a giant buffer and read from that buffer in the shader. And you could do this in OpenGL too, actually. There's nothing stopping you. So the point, though, is that we could completely sidestep that entire part of the Vulkan API. We just say, look, every single model on this level goes in one giant buffer, all in a row, and the vertex shader just indexes that buffer when it's time to draw stuff. This is called vertex polling. You might think that that would be slow. It turns out that, do your own research, profile and stuff, but my understanding is that on desktop hardware, this is basically what's happening under the hood anyway, and there's not really any advantage to the vertex buffers in most cases. You do still want to use index buffers because they allow for some optimizations that wouldn't be possible otherwise. But you don't need to create all these different vertex object types and stuff. You can just put them all in a buffer and you're good. Also, on top of sidestepping dealing with that whole part of the API, you get a lot of flexibility in potential performance because now you have the option to pack your vertex data in creative ways or even just to generate it, right? Because if your vertex shader just gets a vertex instance, it could go index into your buffer to get the vertex positions and data. It could also just generate them, right? Like really, you just tell it like draw 100 vertices, and then it could just do some math and decide where they are. You don't even need a model in the first place sometimes. So by using vertex polling, you just get a lot of flexibility to kind of just be creative with where your vertex data is coming from. Okay, uniforms. In OpenGL, right? You often are calling like GL uniform postfix to set basically a shader parameter. You know, maybe you're drawing an object and you want to make it red, so you first call GL uniform color, comma, you know, your red color, and then like you draw the object, and then when you draw it again, when you make it green, you call it GL uniform to change it to green. You can do this sort of thing in Vulkan too. It's a little bit more complicated. You got to learn about descriptor sets, descriptor set layouts, pipeline layouts, and if you're writing Vulkan, you should learn how this stuff works. It's worth understanding the details. And you could end up building a system that is very similar to OpenGL. It's going to be more code, it's going to be more complicated, but you can do it and it'll be fast. Alternatively, though, you could just put all of your uniforms for the entire scene into one big buffer and then index it in your shader, just like we did with the vertices. And turns out that's like, you know, pretty fast and really simple, and now you don't need to use a lot of the API. I mean, you still need a descriptor set, but you just need one. And this is going to also let us do a bunch of cool stuff on the following slides that wouldn't be possible otherwise. This is called bindless rendering. The idea is that instead of having to bind a bunch of stuff in between each draw, you just say like, look, here's all my parameters for the entire scene in one big buffer, and now you don't need to bind things all the time. You don't need to call into the driver, which means that you don't have this point of potentially variable performance, right? Because when you call into the driver, that's not your code. You don't know exactly what it's going to do, and it might be slow. If you just put everything into a buffer, then that's all your code. You have a memory mapped buffer. You just write to it in your language of choice. And you know, if you're working with other people, they don't even need to be graphics people. You just tell them, look, this is the layout for the buffer. You don't need to know Vulkan. You don't need to know rendering. You just need to know what type of data is supposed to go in this buffer that's going to be rendered, and then any code in your engine, you just write to that buffer. And so, yeah, I mean, all of your per object configuration, just stick it in a buffer, and it sidesteps all of that complexity as well. Let's look at draw call generation. So a common thing when you're writing older APIs is to try to kind of optimize for less draw calls, right? It's like you can only draw so many things. Every time you do a new draw call, it you know, takes some more performance. I forget how I laid this slide out. Oh yeah, so what you used to do in the older APIs, what you had to do, I think they got extensions for this stuff too, but what you used to do is just one draw call per object. Maybe you use instancing if you have a bunch of the same object. But you can actually use a feature called draw indirect to also avoid this. You're going to see a pattern here. It seems like almost always my answer to everything is fill a buffer with data and send it to the GPU, because that's what we're trying to do, right? Like that's what the job of the GPU API is. It's to communicate stuff to the GPU. So yeah, for draw call generation, we aren't going to draw individual objects. We are, again, going to put all of the draw arguments into one big buffer and then tell the GPU that's what we want you to draw. This is called draw indirect. So the idea is when you draw an object, you typically pass in a few arguments like what vertex to start at, what vertex index to end at, a couple other things. You just put all of the arguments that would go into that function into one big buffer, and then you call draw once, and it will just iterate through the buffer and draw all of those things. This is great in terms of, again, you can just, any part of your code can do this. It doesn't need to interact with the GPU API. If you're supporting multiple different GPU APIs, this part's the same. You don't need to abstract anything away, but also like you can do this from multiple threads. You can even do this from the GPU. So you know, there's cool fancy things people do where they'll do like occlusion calling on the GPU, and then they'll emit like which objects they want to draw into this list from a compute shader. This is like a super flexible way to do rendering, and in my opinion, it's a lot easier. You just put all the data in a buffer, send it to the GPU, hit draw. Okay, let's get to materials. So again, this is a source of potential complexity, right? We could say, okay, every new material is going to get a new pipeline object, right? So we're going to have like a new shader that has new logic for that material, and then a bunch of new configuration options. And then we're also going to have to like sort our draw calls, right? Because we don't want to be changing shaders all the time. So okay, we sort all our draw calls by material type, and then we like issue one draw indirect call for every material. And then, like, you know, you can totally do that. There's nothing like wrong with it. But there's another option because we already sort of have materials with what we've described so far, right? We were just talking about uniforms and how you can put all of your arguments for like a shader into a buffer. There's no reason we can't use that for materials. You can just put a giant switch statement in your shader where you switch on a material index, and then you just run different code depending on which which material you're on. So if you're on a shiny object, you put the shiny index and it runs that function. And if you're on a matte object, it runs the matte function. And I know what you're thinking. Conditionals in my shaders, Stack Overflow told me that was slow. This guy doesn't know what he's talking about. I'm not going to pay attention to the rest of this talk. But it's important to understand like why are conditionals slow. And the gist of it is that GPUs are giant SIMD machines, and they want to run the same instruction on multiple data sets. If you have a conditional, and this pixel runs this side of the conditional, and the pixel next to it runs the other side of the conditional, well, that's not really a thing it can do. So it's going to end up stalling while it like waits for one of them to finish. And then if it's like an else, maybe also have to stall again while it waits for the other one to finish. That's slow. You don't want that. But we're talking about materials, right? And materials, we're talking about like per object materials, which means you're always taking the same side of the conditional within an object, which means you never have to stall. So in the case of this approach, this Uber shader approach, which is what people typically call it, it's not, a conditional is just a conditional. Like, is there a cost to it? Yeah, there's a cost to a conditional, but like, it's not the, when you read people saying, don't put conditionals in your shader, they're gonna make everything slow. This is not what, well, it's either not what they're talking about or they're just wrong. So yeah, you can totally just put a giant switch statement in your shader and switch on the materials, and now you just have a single pipeline for your entire game, which also sidesteps all the complexity of having to like cache pipeline objects so that you do like, between runs so that your load times are faster because you just got the one anyway. So yeah. Some details here on how I do materials. Don't have to do it this way, there's many ways to do it. So this is a little bit of pseudocode because GLSL doesn't actually have U16s, unfortunately. I pack the U16s into a U32, but the gist of it is that each object that I draw has a material index, that's the thing we're going to switch on to decide which function to run. It has 16 bits of just miscellaneous material data that's interpreted per material. So it might be that one material uses it for a completely different thing than another. It's just up to the function that draws that material to decide what to do with it. And then it has a second piece of miscellaneous data that's 32 bits, which could have whatever in it, but often you're going to need more data, like a matrix or something, in which case this will actually be treated as an index into a separate area of memory that has larger data. And the reason I do that is because you want to pack all this data tightly. If you tried to put all of your material data in a single material instance struct, you'd have to make it big enough for the worst possible case. And then all of your simple objects that need very few configuration parameters would still take up all of that space with padding, which would be a little goofy. So the idea, this is just like stuff from Andrew's data-oriented, practical data-oriented design talk. It's like the same sorts of ideas here. You can do all that stuff on the GPU too. So yeah, the idea is you put some data per object in a list of these material instance structs, and then whenever you need more data that doesn't fit, you just treat one of these as a pointer into some other buffer where you store that extra data. Those two lines at the bottom there are just a little useful trick if you happen to be writing GLSL. GLSL doesn't actually support unions, but you can kind of accomplish the similar thing by binding multiple variables to the same binding number, and then they'll just get reinterpreted as whatever type you list them as. My understanding is this is like fully allowed. It's very, very convenient. You do have to make sure you do your math right so that the index is actually the correct index, right? Or to store byte offsets or something. But yeah, this lets you store all of your data very compactly and get it to the GPU very, very efficiently. So yeah, I mean, that's the summary of my rendering approach. It's pretty straightforward, right? You generate a buffer of all of your which vertices you want to draw, just like the start and end indices. You generate a buffer of all of the per object configuration, and then you generate that separate buffer for data that didn't fit in the previous one for bigger material data. And then you issue one draw call for your entire scene that then just goes through and draws all of the objects. So yeah, we just fill up a few buffers, memory map buffers, and then we tell the GPU go, and it does. And it's really not that much code. I should have maybe counted before I came here so I could tell you the number, but that triangle example was maybe it was 1,100 lines or whatever. I'm pretty sure my renderer with all of these features is, I don't know, it's like 2,000 or 3,000 lines of code, and it has all this flexibility, right? Like it has a full material system. You can like fill in different logic for different objects. It has I didn't mention it. There's a few things I skipped, but it has instancing. It has all kinds of stuff, and it's just not really that much code because ultimately all we're doing is filling buffers, sending them to the GPU, and drawing them. So what does this get us? Minimal driver overhead for one. All the binding of resources has a cost. All of the individual draw calls have a cost. Minimal API surface area, which just makes my life easier as one person writing a renderer. And when I want to port to other APIs, it makes my life easier, right? Because when I want to port to DirectX, or if I want to port to whatever the NVIDIA API on Switch is or something, right? Like there's less stuff I have to implement. I just have to make sure I can get my buffers to the other device. It gives us the flexibility to generate draw data from multiple threads or from the GPU. So I didn't really go over it, but in my engine right now, I actually do issue more than one draw call, but only because I have a thread pool, and I do this work simultaneously in all threads. So like, each thread pool task issues a draw call just because, hey, why not? Why not do it all in parallel? And if you're working with OpenGL, trying to do stuff in a like multi-threaded fashion is like a little tricky sometimes. OpenGL isn't really exactly designed with that in mind, or at least wasn't from the beginning. There's some ways to make it work. Here, it's just like not a big deal. Don't get me wrong, Vulkan does let you do multi-threaded stuff. You could use a more like API-centric approach where you're like working with more parts of the API and do it multi-threaded in Vulkan. It is very well designed to allow for that. But like, you don't even need to think about any of that. Like, it's just all the normal rules you're used to for multi-threading because you're just filling up your own buffers with data and then kind of all in one go telling it what to do with them. So yeah, we did skip over a few things. I didn't talk about instancing. And like, yeah, in your actual game, you might have extra passes for post-processing and stuff. And so yeah, you probably end up with a couple more pipelines than just the one. But none of this stuff really changes the overall strategy. Like you can use this approach and kind of add on these extra features. So okay, this all sounds great. Is it actually fast though, right? Like, am I just pitching you a simpler way to use Vulkan that is also slower and means you should have just used OpenGL to begin with? I'm going to show you a little demo here. Start out with just a screenshot, nothing impressive here, but I want to explain what's happening. So here we have a bunch of individual game objects on the screen. It's not like a particle system demo. If I was going to do a particle system, I would just do it fully on the GPU and put 100 bajillion particles and it would go fast. But the point of this here is that I have a bunch of different like game objects. So if you have an entity component system, these are your entities. Whatever your way of organizing your game objects are, this is them. And they exist on the CPU, and I'm going to send them from the CPU to the GPU every frame. So all of the, I'm not caching any data. All of the colors, the positions, and everything getting sent every time. And I'm running this on like a 6-year-old laptop or something. And so I want to see like how many objects can I render using this approach, and still hit 60 hertz on this 6-year-old laptop I'm testing on. And they all potentially have different materials and everything too. Okay, so we started out with 100. This is it? It's not showing up there for some reason. I'm supposed to have a slide with a picture with some more dots. Ah, there it is. So okay, I think this is 1,000. Still getting 60 hertz. Okay, we got 10,000. Here, I got a question. How many pixels do you think there are on like a 1080p screen? It's like what, like 2 million? Okay, fuck it. Let's do 2 million. Can we get that video on here? Okay, yeah. So I mean, I don't know. Does your game need to render more objects than there are pixels on the screen? No? I didn't think so. So obviously this is like a goofy demo. The objects are all very simple, but the point is that the cost of getting the data to the GPU is cheap. Obviously, if there was 2 million objects with fancy reflections on them, sure, it wouldn't run 60 FPS. But that's fine. That's your shader code that's responsible for like the fancy effects. The point is that like we're trying to figure out today, how do we use Vulkan to get the data to the GPU so that we can run it? And clearly, if this approach can draw 2 million objects at 60 FPS on a 6-year-old laptop, then yes, it's totally fine. This is a totally realistic, pragmatic way to get to the data to the GPU, and then you can do all the normal optimizations you would do on the shader side to make your shaders fast. And also, like, you can just not draw 2 million objects, and you can cache data. And like, you know, if you're doing a particle system, don't do it this way. Just do it in a compute shader. But the point is, that's possible. So this works. This is a totally viable way to render your entire game. And lots of games do use this kind of approach. Okay, so what makes a good API? Well, you know, lots of people have different opinions about this. Not trying to say mine is the only correct way of looking at it, but I think that like going through writing this graphics API abstraction and learning Vulkan has kind of made me think of APIs as just a way of communicating with an underlying system. You know, as a low-level person, often that underlying system is hardware, but it doesn't have to be. The underlying system could be another software system. And I think, you know, it's not the only way to look at it, but I think that it's useful to think of APIs as being like well-designed when they facilitate communication with an underlying system, and poorly designed when they obstruct it. And as a consequence of that, if you have an API that's doing a good job at like letting you communicate to the underlying system, but you're still having trouble completing your goals, then it's probably not the API that's at fault, right? It's probably either the underlying system, or it's that your goals aren't meshing well with that underlying system. So, you know, Vulkan definitely isn't a perfect API. I have nitpicks and criticisms, but I don't think being low level is an imperfection. I think the low levelness of Vulkan is a huge improvement, and I think that going forward, my renderers, despite having many more lines of code, are going to be much simpler. So yeah, that's kind of my takeaway. Maybe think about designing for hardware instead of for APIs. So I got some useful links here. If you are doing Vulkan, you probably often will need to look up info on different GPUs. VulkanGPUinfo.org is a super useful resource. The QR code here also links to the slides, so if you want to go back and look at those speaker notes for anything, you can. VulkanGPUinfo.org lets you look up like how many GPUs support such and such feature that I'm considering using, what type of memory does this GPU have, what type of memory does that GPU have. The Steam hardware survey linked below that is also great. It's a good way of figuring out like which GPUs are players using in practice if you're shipping games on desktop. Some Vulkan tutorials. I wouldn't like necessarily ship the tutorial code, but they're great ways to get started understanding the APIs. And then some useful tools, probably you all know about them, but if you don't, you should try out RenderDoc. You should try out Tracy. DRM GUI is great. And if you're using Zig, the Snectron's Vulkan Zig wrapper is really nice. So that's it for me. If you want to support me, a great way to do that is picking up my game Way of Rhea, which is on sale right now on Steam. I also have copies in person. If you're interested in more of this kind of stuff from me, I have some talks online at that address, newsletter, stuff like that. Got a GitHub linked there where the graphics API abstraction I'm working on will be public soon. And then I have a bunch of other little game tools and stuff, or wrappers for existing game tools that I'm putting up there. That's all I got for now. Happy to, I think we got a bunch of time for questions.
You can sit down on that chair right there. Get comfortable.
All right. I take privilege for the first question.
Sounds good.
Wow, I have a lot of thoughts on this. I might have to ping you even like after this talk, but because I told you I'm writing my own terminal emulator, and I started using Vulkan, then switched to Soko once I met these barriers about barriers.
Yeah, once you literally met the barriers, and you're like, geez, what the heck is that?
Yes, but you mentioned uniforms, which is true. I always had that feeling of if I'm updating shaders by calling GL uniform once per frame, like I'm updating a color, yeah, exactly, some value, and I'm doing this matrix transforms or whatever. I always felt like that was like doing that one per frame felt like a lot of overhead. That felt a little wasteful. So I did like that about Vulkan, that you have this uniform. I never even went to descriptor sets. I went to uniform buffer objects right away. You know, it's just a large addressable memory, huge byte arrays. Love that, right? And you can do even partial memory writes, and you can decide when to flush it. I think you told me you can decide when to allocate. Even I love that control. For sure, and that's simple for the driver, for sure, because now it's all passed to you. I like that simplicity. But what would you say about, like, even then though, like, would you recommend somebody like myself on the just 2D side? Because terminal is just text, right? It's just some text and some icons. I'm pushing 2D quads. Would you still recommend I try and give Vulkan a chance again, or what's your judgment call on that? Because I would still have to do some work to grok everything, right? But
Yeah, so it's tricky. I mean, I would say like, you have a project you're trying to ship, and if what you're doing is working for you, then, no reason to burn a bunch of time undoing it and trying something else.
fair.
But I would say like, to someone in the game space, I might be a little, not that you couldn't benefit from Vulkan,
Sure.
but I might kind of push someone doing games a little more strongly to try using the modern APIs, and the reason being that like, I worked with OpenGL for a long time, and a lot of these techniques I'm describing, like you could do in OpenGL, but I never realized because it's very hard to learn what's actually going on. When it's kind of like if you like learn programming using Python, and hey, no shade to anyone learning programming using Python.
I'll give you shade.
In fact, it's probably in fact, it's probably a good way to learn. But there comes a time when you're like, okay, like I kind of want to know what the computer's doing, and like, I mean, you're not going to be able to figure it out. It's like even though it's like a easier language to do some things in, like you're not going to understand what's happening under the hood because it's not like exposed to you. And like, and then the thing is, if you ask a low-level programmer to write Python, they can actually probably make it pretty fast because they know how it's actually working. Mm-hmm. And so if you asked me to write OpenGL right now, I probably could make that demo like the same speed in OpenGL. But if you had asked me to make that demo in OpenGL with no compute shaders or anything prior to messing with Vulkan, I don't think I would have succeeded at it because I just really had no idea what was happening. So if you're someone who like GPU programming is going to be important to you going forward, then I would say like I really recommend giving this stuff a shot because it'll make stuff make more sense. In your case, like you have a thing that you need to get done and it's just a piece of the puzzle. So like, whatever. If it seems like fun and you have the time to kill on it, I'm happy to answer your Vulkan questions. If you decide, look,
if I have an ear with you, then I might give it a shot again. Yeah, cool. I would like the chat to answer this question for me too, and I know you can answer it, but I want to ask other questions from the audience. I'm curious about Vulkan extensions, and I know ever since I did this Vulkan attempt, there's been a lot more extensions that to the point that almost feels like OpenGL if you really want to, with all these layers of there's validation layers, there's extensions. Like, is that really true, and is that worth it? Right, like to even sounds like you want to say something about that. Yeah.
Okay,
go for it. Yeah.
So I would say like first of all, like a few different things. One thing, it's only slightly tangential, but I forgot to mention it earlier. If you're doing Vulkan, like turn on the validation layers. Like in OpenGL, if you make a mistake, you can call like GL get error and like kind of find out about it. In Vulkan, it's like you can turn on these layers where it'll just like take all your Vulkan calls when you're in like a debug build and filter them through a separate layer which like will check it'll check like you pass the right parameters and stuff, but also like it'll check like for like just common mistakes that are easy to make that like would be maybe hard to I can't think of a good example right now, but they're going to catch problems and they're going to tell you exactly what you did wrong, and then you're going to go, oh wow, I'm really glad I turned that validation layer on.
Right.
I was going to end up with crazy flickering bugs I couldn't figure out, but the validation layer said, hey, don't do that, your synchronization's wrong, and you're like, oh yeah, you're right, actually it is. But yeah, in terms of like extensions and stuff, there's two things I'd recommend. There are a bunch of useful extensions. If you're trying to ship something that'll like work on a bunch of computers, I recommend looking at that database that I linked because it'll tell you like what the support is like. Though consider that some entries in the database may just be from before the extension was released or something, so it might say they don't support it. But then if you look at like a newer sample from the same GPU, maybe it will support it. So the percentages might be a little wonky. But you look at what's supported, and then another trick is that I just look at what DirectX can do, even though I'm writing Vulkan, because DirectX is like Vulkan is trying to support a lot more devices than DirectX, so there's a lot of features that are optional or that are only available through extensions, whereas DirectX is like, okay, it's like Windows and Xbox. So if I look at something and I'm like, DirectX has that capability built in, then I pretty much just assume, okay, probably all of my target machines have the Vulkan extension too. That's not 100%, but like it's a good jumping off, like a good way to make a judgment call of like, is it worth looking into? Because if you look into like DirectX doesn't have it, then you're like, okay, well maybe this is like a new fancy thing that I can't really use.
Let's try and do 5 minutes of chat questions before we do the bathroom break, okay? So first question, these approaches like, make one buffer and send it to the GPU, that implies that there is now special logic on the GPU to unpack these buffers.
Yeah.
Is that unpacking code hard to optimize? Like if it's arbitrary shader code, how does the GPU do these things quickly when it can't have hardware built specifically for these operations?
Yeah, so I'm definitely not like an expert on like low-level workings of GPU, uh, and I meant to thank Martin for he's I can't see because of the lights all right up there because he answers all my GPU questions, but my understanding when it comes to, and maybe someone who's an expert can correct me if I'm wrong, but my understanding when it comes to like unpacking like Vertex data is that like when you do it manually in your shader, it ends up being basically what the GPU would have done anyway. Like it's sure you told it to do that from the API, but I don't think it's actually like taking a different path on desktop. Maybe that may not be true everywhere. In terms of other data, like uniform data and stuff, I think it just like it depends so much on like exactly what you're doing that I don't have like a general answer. But I would say that like if you're taking a 32-bit integer and you're splitting it into two 16-bit integers, like that's not an expensive operation. And like so yeah, like the more clever your encoding gets, the more complicated it's going to be. But I'm not. None of the encodings I'm using so far are really all that involved.
In the interest of time, I'm curating some questions in case you see that I'm going out of order. This question is from
one other
please,
piece.
please. Yeah.
One thing to consider when you're doing this stuff is whether or not it would be trivially possible for the GPU to prove that what you're doing is consistent across the whole object. So, for example, if you're using something to like index an array, but you're deriving it from like the base instance of like the what's it, GL base instance or something. It's like the GPU knows, or that cannot vary within like the draw, and so presumably it would be trivial for it to figure out, okay, we can reuse that result for the entire draw. I don't know enough about the low-level details to know like when that is and isn't done. I'm under the impression it's done sometimes. So yeah, like I design all of the unpacking to be presumably trivial for it to figure out that yes, the entire object will get the same result here. So yeah, but that's not hard to do though, because you're usually doing it based on your instance index, which
Next question by Rez Mason. Do you have any thoughts on web GPU or the web GPU implementation for indie development? These techniques you showed look as feasible on web GPU as Vulkan or the others.
Oh, fellow Mason. Yeah, I mean, it seems fine. I'm not like, it wasn't like, I'm trying to figure out how to put this. All these APIs seem really similar. I think that when I was looking at it, there was like, maybe it was like indirect drawing or something that like wasn't fully supported, or I feel like there was like one of these features that like wasn't fully supported there, and it felt a little silly because I was pretty sure that the underlying hardware all supported it.
Yeah.
I'm personally not using web GPU just because I don't ship on web, and I understand that web GPU works on desktop. But like every platform that web GPU works on desktop, Vulkan also works on, and it's like what the like, all of my graphics debuggers work with Vulkan. It's what the like graphics card vendors are like giving advice about directly, and I don't know. I don't want to go through Google stuff, and I don't want to do text shaders. I don't understand why they had to do text shaders. I think maybe you don't have to anymore. Maybe they walked that back. But I think it's perfectly viable. Like, all these APIs are very, very similar to each other. It's just I do get a lot of people asking me like, why make an abstraction layer when you could just use web GPU? And I think that's a little misguided because it doesn't like, I need to work on PC and console. If I just needed PC, I would just do Vulkan, and then I would use Molten VK for Mac. I'm not even shipping on Mac anyway, actually. And if I want to do consoles, then, well, I'm gonna need to do something else besides web GPU or Vulkan or whatever. So. But it works. You could totally just use it and do most of the same stuff.
This one comes from Redline. Is there a Vulkan tutorial that isn't an object-oriented monstrosity?
Yeah, not that I'm aware of, unfortunately. It's a little frustrating because I think that half the time I spend when I'm reading like a tutorial for like a new Vulkan feature I don't know is just trying to untangle they built like abstractions for it like up front that aren't the abstractions that I want, and I have to like undo them to understand what's happening, and then so yes, sorry, I don't have any good recommendations there.
I personally rewrote every example from vulkan-tutorial.com into vanilla C from C++ and C++ 17. Not easy.
My recommendation would be yeah, undo all the object-oriented stuff, but don't try to replace it right away because it's too hard at the beginning to understand like it's too hard to see the forest for the trees until you've like gotten the triangle working. So like I would build like 0 abstractions, and I would like just get even when they tell you like you should build an abstraction for this, like don't do it. Get to the point where you have the triangle, and then that's your time to go, okay, I have all of the parts. Now I can sit down and think like, how can I actually chunk this up in a meaningful way? And I think you'll do a much better job at that point than if you try to do it from the beginning.
The final lesson in the tutorial, one of the final lessons I think is to import some 3D model, like some OBJ model. And I remember I was like, oh, it's just, some OBJ models have duplicate vertices in the data, so you can just deduplicate by doing a mem compare. You loop, mem compare and discard. I was like, oh, that's exactly what they're going to do, right? No. They import an unordered map. They do custom template specializations with hash functions, so you can index into vertices as an array.
No, what kills me?
I just want to render. Sorry, go ahead.
Oh no. Well, what kills me is like I don't know. Your game shouldn't even be doing any of that, right? Like convert the data to a format that you can just upload and do no processing. And don't get me wrong, like you do need to at some point do the deduplication. And yes, it should be in an offline tool. And no, the beginner trying to learn the API for the first time doesn't need to learn how to write that tool. But that's exactly my point. Like if I was to write a tutorial for Vulkan. And I'm not like hating on the people who write tutorials. I'm very grateful for that to them because hey, that's how I learned Vulkan. But if I was going to write a Vulkan tutorial, what I would do is I would give a model file in a format, like in a binary format, where it's just literally the list of positions with no header and nothing else, and be like, look, for the purposes of this tutorial, just load this into memory as is and do 0 processing, and then maybe have a separate stage later where I show the code for how I made that file. And then don't do it with hash maps and stuff.
Couple more questions and we'll conclude. And there are still more questions that I hope you can answer in the chat later. So from Seth, thank you for your question. Have you used Soko? Can you do bindless rendering and vertex pulling there?
I haven't used Soko. It looks great. At the time that I looked at it, and this may not be true anymore, at the time I looked at it, it was like, maybe not the last generation of APIs, but like the in-between one, and I wanted to be on like the absolute latest thing, so I was like, okay, I'm just gonna do it myself. But it looks really great. I do not know whether or not you can use these techniques there. I would not be surprised in either direction.
Question from Mige. What was the alternative for the... I think he's asking for something. What was the alternative for the Vulkan memory allocator library?
Oh, yeah. And another place where like that library looks great. I just make like one big allocation like up front. So it's like, one per memory type. So, okay. The simple version is I make one big allocation, for example, on level load, and then I just bump allocate into that because you never really like free stuff, right? Like
interesting.
Like how often do you need to remove a texture from the GPU, right? Like an individual texture, right? Like you probably remove the whole level. Now, if you're doing some kind of streaming thing, then you do need to remove stuff, but you could just remove a whole chunk or add a whole chunk. If you really are doing something fancy where you're like, having like streaming in higher resolution versions of textures, you could just like leave room for them in that buffer. So the idea is that you don't need a heap allocator because I really don't like heap allocators, like in general. Like it's in a high level language, it makes sense. But when you're doing low level stuff, you almost always know more about the lifetime of your objects than a heap allocator does. So you can almost always do better. And it sounds like you're like doing more work then, but like the answer is almost always like a bump allocator where you just like add stuff like you say here, the first object starts here, and then you just add the next one after, and then the next one, and they're all just next to each other. And as long as you get the alignment right and stuff, like that's fine. And it's so simple and it's so fast. So that's what I do. The wrinkles come in when, first of all, like the alignment restrictions can be different per GPU. So you do have to do some work to get this right the first time. So you got to read about like what the alignment rules are. And there are also different memory types. So it's not really just one allocation. You need to make a few allocation based on the different types of memory. What I recommend here is look at the memory types that DirectX exposes, because it's a simpler way to kind of understand. Like Vulkan will give you like 10 different flags, and essentially what I ended up doing was just re-implementing the same ones DirectX gives. So I have like an upload buffer, a readback buffer, and then like a static buffer, and then also like a base address register upload buffer for like smaller, faster uploads, or big ones if it's resizable base address. Anyway, there's like 3 or 4 different like memory types, and then within that you might need different stuff for like vertexes versus images and stuff. So there's like details to get right, but the point is that you make your big allocations up front, and then you just bump allocate into them, and then you don't have to worry about heap allocation and garbage collection and everything.
In the middle of your talk, there was one comment, I think it was from Ruben, who said, your talk is a great high-level introduction to boneless rendering. And now there's a whole running gag there that I hope you enjoy after this talk. Well done, Mason. Round of applause. Round of applause. Nobody but you could probably
I was
tempt
clapping
me.
for the boneless joke, not for myself. Yeah, boneless rendering is when you do like the ollie, but you put your foot on the ground while rendering.